Okay, so welcome guys. So in this video, let's try to prove this fact. I mean, I think this is the first important theorem when I learned the advanced calculus. So the idea is that we have the an, which is the sequence in the real number. So yeah, let's just take it, and the bn also a real number. I think this will also work for complex number, right? But when I do the definition, I only prove the case when a real number. Okay. Or I think even though it's a real number. Okay, so let's prove the first one say that if you add a and a bn, then there's a new series. Also, it's a new sequence. Then you get a plus b. Okay, and then this is a minus b, a n minus b, and then you a minus b, and you times it. Then you take a limit, become a b, and you divide it. Then you just a divided by b if b is non-zero. Okay, so the first one is very easy because the idea is that I can let a n plus b n minus a minus b, right? So this is just a n. This is what this will less than that's equal to a n minus a plus b n minus b to b. Right, so since that limit n goes to infinity, a n is a, right? So for epsilon greater than 0, I can choose, let's say, n1, such that when n greater than n1, then then your a n minus a is less than epsilon divided by 2, right? So same as the b, same as our bn. So now limit n goes to infinity, bn is b. So for a epsilon greater than 0, there's this n2, right? Finally, so bn minus b is less than epsilon divided by 2. Okay, so this is less than epsilon plus divided by 2 epsilon, right? So if we just choose n larger than a maximum of n1 and n2. Then it's enough. Okay. So this is the first one. Okay, so the second one say that a minus bn is a minus b. Okay, so the idea to prove is just right. The idea is that we just change bn to negative bn, right? And so all we need to do is that proving this one. We only prove this, right? But this is just from a definition. Right, because when you times the minus one, that we counted when we compute, right? So bn minus b is same as negative bn plus b. So it's negative bn minus b, right? So if this term can be suppressed by epsilon, then this term can also be, right? So this is basically exactly the same thing. Okay, so the next is we prove the third. Okay, so the third is usually probably the difficult one, right? So okay, so to prove the third, let's prove a lemma. So this lemma, I think I will easily prove. So lemma is that if an converge to a, then an is bounded. So basically, the convergence sequence, sequence, right, is always bounded. So there means that it is m such that an is less than m. So the idea is that right, if we for epsilon larger than 0, there's a n1, right? So if n is larger than n1, then I can choose that an minus a is less than epsilon, right? So that means an is less than less than 1. So that means an. Okay, so let me just write carefully. Right, so that means an minus a is less than epsilon, right? So that means right, either this one is correct, right? So this one, right? So an is less than a plus epsilon or a minus epsilon. Okay, is it correct? Hopefully, yeah. So right, so that means so this just means that if this is a, right, then when n goes to very large, then all of the a will bounded by something, right? Bounded by this one. So this is a minus plus epsilon, a minus epsilon, and all your a will fall in this range. Right, so let's consider m to be the maximum of the previous one, that's a1, a2 up to an1. Right, and with this a minus epsilon and a plus epsilon, it's clearly m is a bound, right? because that all the an larger than it will fall into this region, right? But previously we only have finite, right? So these are all the total finite number, right? So I call it m, so an is bounded by n, so an is bounded by n. Okay, so we only need this lemma, then we can prove the rest. Okay, so the idea is that let's say n bn minus ab, right? Idea is that we want to control this term, and this term can be written as an bn minus an b plus an b minus ab. So this is an bn minus b plus b an minus a. Right, so control this term is not difficult because I already said a is bounded, right? So there exists m bn minus b. Right, so an is bounded. Oh, by the way, I previously just proving that an is bounded, right? But you can just change it to absolute value, because when you take an absolute value, the original sequence still converge. Okay, so right, so right, they can take an absolute value. Right, and then we just carry it, and then this is also right, so n minus a. So idea is that I can find n2 such that when n larger than n2, I can let bn minus 2b to be less than epsilon divided by, let's say, 2n2. Oh, sorry, it's 2m2. 2m, not 2m2, 2m. And for the n1, right, if n is larger than n1, I can also let an minus a less than epsilon divided by 2b. So idea is that if okay, so if b is 0, right, then this is all, then we don't need this, right? So it's fine, right? It's still fine. Okay. So we do these two, then we can bound this to be less than epsilon. Okay. Okay, so finally, we just try to compute this. So to the first one, we just try to compute an divided by bn minus a divided by b. So this is bbn minus ban minus abn. Right. So if let's just easily make a guess, right? So if n is very large, then bn, right, is so idea is that bn is very close to b, right? So that means this term, right, is close to like b squared ban minus abn, right? And the same reason is that you can control this ban minus abn bn squared. So you can use our previous things, right? So all we need to prove is lim an divided by b. It's just what? It's just a divided by b, and this is what we already proved by the sense reasoning. Bn go to negative bn, right? There's just some constant, so this term is basically go to a divided by b, and the same for this term, right? This is just constant, right? So you can use the same way, right? But now everything is clear because when n goes to infinity, bn is close to b, right? So this term goes to b as the arrow can be arbitrarily small, then you separate into two terms, right? Then you go to you use the same way. So ideally, you just need to use 3n, n1 to n3, and the epsilon bound, then you can easily prove it, right? So basically, this is already the proof. Okay, so the proof is done. Okay, and right, and I want to also prove things that if limit n goes to infinity, an is a, then if you take the absolute value, then this is a, right? And the proving idea is that just notice this, right? So suppose I use absolute value an minus the absolute value of a and take the absolute value, then it will less than this, right? This is the triangular inequality. Okay, so if this term can be bounded by epsilon, then also this term can. So proof is done. Okay, and I will see you guys in the next videos. If you're interested, you can go to my real analysis series in my channel list.